Welcome to G Fun Facts Online. Today we are diving deep into a subject that sounds like science fiction but is rapidly becoming science fact: the world of quantum acoustics and the rise of the mechanical qubit. For the better part of the 21st century, the race to build a functional, scalable quantum computer has been a duet played by two primary actors, which are electrons and photons. We trap ions in electromagnetic fields, we steer electrons through superconducting loops, and we guide pulses of light through fiber optic cables. These particles, matter and light, have been the undisputed soloists of the quantum revolution. But a new player has entered the orchestra, one that is older than the concept of computing itself, but entirely new to the quantum stage, and that player is sound. This emerging field is known as quantum acoustics, and its fundamental unit of information is the mechanical qubit. To understand why this is revolutionizing the field, we first need to adjust our understanding of sound itself. To a classical observer, sound is mundane. It is a pressure wave moving through air or a vibration traveling through a solid. But if you zoom in to the atomic scale, sound reveals its quantum nature. Just as light is composed of discrete packets of energy called photons, sound is composed of discrete packets of vibrational energy called phonons. For decades, phonons were viewed merely as pests in the quantum world. They were sources of heat and noise that decohered fragile quantum states in superconducting processors. They were the enemy to be suppressed, frozen out, and shielded against. However, in a paradigm shift that has accelerated dramatically between 2024 and 2025, physicists have stopped fighting the phonon and started controlling it. Leading research groups at institutions like the University of Chicago, ETH, Zurich, Caltech, and Stanford have demonstrated that mechanical resonators, which are essentially tiny, vibrating drums and strings, can be placed into entangled quantum states. They can store quantum information for seconds, which are lifetimes vastly longer than their electromagnetic counterparts. Most importantly, they can act as universal translators, converting the language of superconducting quantum computers, which is microwave energy, into the language of the quantum internet, which is optical light. To really grasp the physics of quantum sound, we must discard the intuitive notion of sound as a continuous wave. In the quantum regime, a mechanical oscillator, whether it is a nanoscale beam or a surface wave on a crystal, has energy levels that are quantized. It cannot vibrate at just any amplitude. It can only contain integer numbers of phonons, like 0, 1, 2, and so on. The transition from a vibrating guitar string to a quantum mechanical oscillator is defined by temperature. At room temperature, a 5 GHz mechanical oscillator is swamped by thermal phonons from the environment. The noise of heat drowns out the signal of quantum discreteness. But when cooled to millikelvin temperatures in a dilution refrigerator, the thermal energy drops below the energy of a single phonon. The oscillator settles into its ground state, a state of 0 phonons. From this silent vacuum, researchers can inject a single quantum of vibration, a single phonon. This is the acoustic equivalent of a single photon, but instead of an oscillating electromagnetic field, it is a collective oscillation of billions of atoms in a crystal lattice. One of the most compelling arguments for using sound in quantum systems is its speed, or rather its lack thereof. Light travels at approximately 300,000 kilometers per second. In the time it takes a quantum processor to perform a single logic gate, which takes nanoseconds, a photon has traveled meters, leaving the chip entirely. This makes feedback operations, where you measure a particle and then adjust it based on the result, extremely difficult with light. Sound in solids, however, travels about 100,000 times slower than light, roughly 3,000 to 11,000 meters per second, depending on the material. A microwave frequency phonon at 5 GHz has a wavelength of less than a micron, meaning an entire complex quantum pulse can be contained within a device the width of a human hair. This slow speed allows for in-flight manipulation. Researchers can launch a phonon, perform an operation on it while it is traveling across a chip, and catch it at the other end. This capability is unique to the mechanical domain and opens up new architectures for signal processing that are impossible with purely photonic systems. Now, a mechanical object, no matter how small, is electrically neutral. So how do we control it with the electronic circuits of a quantum computer? The answer lies in piezoelectricity. Materials like lithium niobate and aluminum nitride are piezoelectric, meaning when you apply a voltage across them, they deform. Conversely, when they deform, they generate a voltage. By patterning metallic electrodes on top of these materials, researchers create interdigitated transducers, or IDTs. When a microwave electrical signal from a superconducting qubit hits the IDT, it is converted into a mechanical wave, a phonon. This process is bidirectional and coherent, meaning the quantum phase of the electrical signal is perfectly preserved in the mechanical vibration. The critical metric in these systems is the coupling rate. If the coupling is faster than the rate at which the phonon decays, the system is in the strong coupling regime. In 2024, devices reached cooperativities exceeding 100, allowing phonons and qubits to swap information back and forth hundreds of times before the signal is lost. There are two main ways to guide these phonons. First is surface acoustic waves, or SAW. These are ripples that travel along the surface of a material, exactly like earthquakes or ocean waves. They are easy to access and manipulate because they are on the surface. This is the preferred mode for flying qubit architectures. The second is bulk acoustic waves, or BAW. These vibrations travel through the body of the crystal. Because they are buried inside the material, they are less sensitive to surface imperfections, leading to higher quality factors. A specific type, the high overtone bulk acoustic resonator, or HBAR, essentially bounces sound back and forth between two surfaces of a chip, acting as an exceptionally long-lived quantum memory. A mechanical qubit is rarely just a vibrating beam. A pure harmonic oscillator is linear, meaning its energy levels are equally spaced. To function as a qubit, which requires distinct 0 and 1 states that can be manipulated without accidentally triggering state 2, you need non-linearity. Therefore, most mechanical qubits are hybrid systems. They consist of a linear mechanical resonator coupled to a non-linear superconducting qubit, usually a transmon. The transmon acts as the controller or the non-linear key. The transmon creates a superposition of electrical states, and via the piezoelectric coupling, this electrical superposition is mapped onto the mechanical resonator, creating a superposition of vibrational states. Essentially, the drum is vibrating and not vibrating at the same time. Once the state is transferred, the transmon can be detuned, leaving the phonon to evolve on its own. To prevent these precious phonons from leaking away into the substrate, engineers use phononic crystals. These are periodic structures, holes drilled in a pattern or alternating layers of materials that act as acoustic mirrors. Just as a photonic crystal can block light of certain colors, a phononic crystal creates a band gap where sound cannot propagate. By placing the mechanical qubit inside a defect in a phononic crystal, the sound is trapped in a tiny cage, bouncing back and forth with nowhere to go. This acoustic shielding is crucial for reaching the long coherence times needed for computation. Building a mechanical qubit is a feat of extreme nanofabrication. The structures are often carved from lithium niobate, a material known as the silicon of photonics, due to its potent optical and piezoelectric properties. Historically, mechanical resonators had to be suspended, like tiny bridges or diving boards, so they could vibrate freely without touching the substrate. These suspended structures were fragile and, crucially, had poor thermal contact. A laser beam used to read them out would heat them up, destroying the quantum state. In 2024 and 2025, a major breakthrough occurred with the development of release-free mechanical resonators. Teams at Caltech and Stanford developed methods to confine sound in tight waveguides on the surface of a chip without suspending them. They used acoustic impedance mismatch, using materials that sound hates to travel into, to trap the wave. A device sitting directly on a sapphire substrate can dissipate heat thousands of times more efficiently than a suspended beam. This allows researchers to pump the system with higher power lasers for better readout signals without melting the fragile quantum state. Fabrication challenges also include roughness. At the scale of nanometers, a smooth surface looks like a mountain range. Surface roughness scatters high-frequency phonons, causing energy loss. The latest fabrication uses atomic layer etching to achieve surfaces smooth to within a few atoms. Additionally, combining a superconductor like aluminum with a piezoelectric, like lithium niobate, is chemically tricky. Oxides can form at the interface, absorbing the microwave signals. New flip chip techniques, where the qubit and the resonator are made on separate chips and then pressed together with nanometer precision, have helped solve this by allowing each component to be optimized separately. The last 2 years have transformed the mechanical qubit from a theoretical curiosity into a functional technology. In a landmark 2024 experiment, the Cleland Group at the University of Chicago demonstrated the entanglement of 2 surface acoustic wave resonators on 2 separate chips. They used a superconducting cable to link them. They generated a half-phonon state, a superposition of 0 and 1, in the first resonator. Using a pitcher-catcher protocol, they sent half of that state to the second resonator. The result was a bell state where the 2 drums were vibrating in perfect unison, entangled across a macroscopic distance. This proved that sound can carry quantum information between nodes of a network. Another major breakthrough was the demonstration of the acoustic Hongou-Mandel effect. This is a famous experiment in quantum optics where 2 indistinguishable photons hitting a beam splitter always exit together, they bunch up. It is the gold standard proof of quantum behavior. Researchers built a phonon beam splitter using coupled acoustic waveguides. When they sent single phonons from 2 different sources into the splitter, they observed the same bunching behavior. This confirmed that phonons are identical bosons and can be used for linear optical quantum computing schemes, but using sound instead of light. Furthermore, in 2025, a joint theoretical experimental effort demonstrated deterministic phase control of phonons. In photonics, generating single photons often involves a probabilistic process, where you try to generate 1, and sometimes you get 0 or 2. The mechanical system, however, is deterministic. You can load exactly one phonon into the resonator with nearly 100% probability using the superconducting qubit as a loader. This reliability is a massive advantage for error-corrected quantum computing. So why go to all this trouble? Why not just stick with superconducting qubits? The answer is the internet. Superconducting qubits operate at microwave frequencies around 5 GHz. Optical fibers, which carry the world's data, operate at optical frequencies around 193,000 GHz. You cannot simply send a microwave photon down an optical fiber. It is incompatible. This is the interconnect bottleneck. Mechanical qubits are the perfect bridge. A mechanical resonator can couple to both microwaves via piezoelectricity and light via the photoelastic effect or optomechanics. In this process, a superconducting qubit sends a microwave photon to the mechanical resonator. The resonator vibrates, converting microwave to phonon. A laser beam hits the vibrating resonator. The vibration modulates the light like an FM radio signal, upconverting the phonon into an optical photon carrying the same quantum information. The optical photon travels down a fiber to the next quantum computer. In 2025, groups at Caltech and Stanford achieved record-breaking efficiencies in this transduction process using the new release-free lithium niobate devices. They demonstrated bidirectional conversion with less than 1 quantum of added noise, the critical threshold needed to entangle 2 quantum computers over the internet. This technology effectively enables the quantum modem. But the utility of the mechanical qubit extends beyond computing into fundamental physics, particularly in quantum sensing. Because mechanical frequency is determined by mass, a tiny change in mass causes a frequency shift. A mechanical qubit in a superposition state is an interferometer for mass. If a stray molecule, or potentially even a dark matter particle, hits the resonator, it disrupts the superposition. This offers a path to sensors with yoctogram sensitivity, opening new doors for searching for dark matter candidates that interact only through gravity. There is also the potential for phononic quantum memory. Superconducting qubits are fast but forgetful. Their states decay in microseconds. Mechanical modes in ultra-pure crystals can ring for seconds or even minutes. A hybrid architecture could use superconducting qubits for fast processing and then park the information in a mechanical HBAR for storage. This acoustic RAM would drastically reduce the overhead for quantum error correction. Despite the triumphs, the field faces significant hurdles. The heating problem is the primary bottleneck. The transduction process requires strong lasers. Even a tiny fraction of absorbed light heats the device. At 10 millikelvin, even a nanowatt of heat is a problem. The new 2D optomechanical crystals and B-dagger designs help, but thermal management remains a critical challenge for scaling. Then there is the frequency disparity. Coupling a 5 GHz phonon to a 193 THz photon is a massive energy mismatch. The process is inherently inefficient. Current record efficiencies are around 1 to 5%. To be viable for a commercial quantum internet, this needs to exceed 50%. Finally, fabrication consistency is a major hurdle. Making 2 mechanical resonators exactly identical so they can talk to each other is harder than making identical transistors. Nanometer-scale variations in the wall of a resonator change its pitch, requiring complex tuning mechanisms to bring them into resonance. In conclusion, the mechanical qubit has graduated from a niche curiosity to a cornerstone of the future quantum infrastructure. It is no longer just about controlling sound. It is about using sound to control the flow of information in a hybrid quantum network. As we look toward 2030, we can expect to see phononic quantum networks, clusters of superconducting processors connected within a cryostat by acoustic buses, and connected to the outside world by optomechanical transducers. The symphony of the future will not just be played with light and electricity, but with the silent, quantized vibrations of the mechanical qubit. We are learning to play the quantum harp, and the music is just beginning.